By 1945, the war against diesel had already been decided in the boardrooms. General Motors' Electromotive division had spent a decade systematically demonstrating that diesel-electric locomotives could outperform steam on fuel costs, crew requirements, and maintenance intervals. Railroad after railroad was signing purchase orders. The transition felt inevitable, a slow, economically determined erasure of a century of steam technology. New York Central's engineering department did not accept that verdict. What they built in response was, by the formal measurement of the American Railroad's own test protocols, the most thermally efficient steam locomotive ever evaluated on the North American continent. In controlled testing at the Selkirk shops, the New York Central S1b, Niagara converted more of its fuel's energy into useful work than any other steam engine the industry had ever measured. Its operational records showed it covering 1,000 miles between major service stops, a figure that matched and in some conditions exceeded the diesel units appearing on rival railroads. Dynamometer car data from the water level route documented sustained outputs that put the Niagara in a class of its own among steam power. Every single one was scrapped. Not one survives. If the Niagara was the locomotive that finally proved steam could compete with diesel on diesel's own terms, why does it exist today only in photographs and a handful of archive test reports? The answer is not a story about engineering failure. It is a story about timing, institutional momentum, and the particular cruelty of arriving at the right answer 4 years too late. New York Central's water-level route between New York and Chicago was, in the mid-1940s, the most prestigious and heavily trafficked passenger corridor in North America. The line ran nearly 1,000 miles without the steep mountain grades that defined routes further west, following instead the gentle contours of the Hudson Valley and the Great Lakes shoreline. This geography was both an asset and a constraint. The absence of severe grades meant that raw tractive effort, the measure that defined Big Boy and the Allegheny, was less critical than sustained speed and thermal efficiency over long flat distances. What New York Central needed was not brute force, it was endurance. The railroad's flagship passenger power through the war years was the J3A Hudson, a 464 locomotive that had carried the 20th Century Limited with distinction since 1937. The Hudson was a refined machine, well understood by the mechanical department and capable of producing impressive performance on the water-level route. But by 1944, Chief of Motive Power Paul W. Kiefer had concluded that the Hudson's design had been extracted to its practical limits. Heavier post-war passenger trains, faster schedules, and the looming competitive pressure of diesel acquisition required something fundamentally more capable, not merely an improved Hudson, but a locomotive built on an entirely different thermal philosophy. The specification that Kiefer issued to the American Locomotive Company in 1944 was precise in its ambitions. He wanted a locomotive that could sustain 4,000 horsepower at the drawbar across the full length of the New York-Chicago run without degrading. He wanted maintenance intervals measured in thousands of miles, not hundreds. And he wanted fuel efficiency figures that could withstand direct comparison with the diesel units that General Motors was placing on competitor railroads. The specification, in other words, was asking Alco to build a steam locomotive that could defeat diesel not on spectacle, but on the ledger sheet. Alco's response was the S1b, the production variant of the Niagara class, designated 484 in wheel arrangement and named for the falls that the water-level route bypassed. The engineering decisions that defined the Niagara were not dramatic in the way that Big Boy's engineering was dramatic. There was no audacious wheel arrangement, no unprecedented physical scale, no headline-grabbing single number that made the machine immediately legible to a public audience. What the Niagara offered instead was a systematic, almost methodical optimization of every thermal variable in the steam cycle simultaneously. A locomotive engineered not for any single performance peak, but for the sustained, consistent delivery of power over distance. The boiler operated at 290 pounds per square inch, feeding two cylinders of 25.5-inch bore and 32-inch stroke.
These dimensions were carefully selected to balance steam demand against the boiler's generating capacity across a wide speed range, avoiding the thermal bottlenecks that limited other locomotives at sustained high speed. The superheater surface area, 1,745 square feet, was among the largest fitted to any single-engine American steam locomotive of the era, ensuring that steam entering the cylinders carried maximum energy per pound. Every pound of steam the Niagara consumed had been processed through more heating surface than competing designs used, extracting more work from the same quantity of coal before it reached the exhaust. The feedwater heater system, exhaust steam injectors, and carefully calculated front-end arrangement reflected Kiefer's singular focus on thermal efficiency, converting the maximum possible fraction of coal's chemical energy into useful work at the drawbar.
In most steam locomotives of the period, this conversion efficiency hovered between 6 and 8%, a figure that had not improved substantially in decades, and that diesel-electric technology was beginning to exceed through its fundamentally different power cycle. The Niagara, in formal testing conducted by New York Central's own dynamometer car and cross-referenced against the independent protocols used at the Pennsylvania Railroad's Altoona test plant, achieved thermal efficiency figures approaching 12% under sustained operating conditions. The number appears modest in isolation. In the context of steam locomotive development, it represented the furthest the technology had ever traveled from its thermodynamic starting point. The Selkirk, New York locomotive shop records from 1946 and 1947 document what those efficiency figures meant in operational practice. A Niagara assigned to the 20th Century Limited between New York and Chicago, 958 miles, could complete the run on a single water and coal load with margins to spare, arriving at the terminal with fuel reserves that would have been unthinkable in the previous generation of steam power. Maintenance logs from the same period show scheduled shop intervals reaching 1,000 miles between major inspections. Individual units accumulated 26,000 miles of revenue service per month, a figure that the mechanical department tracked specifically because it matched the availability targets that New York Central's purchasing analysis had identified for incoming diesel units. The railroad's own comparative studies, preserved in the New York Central Archives at the University of Michigan, document the assessment directly. In a 1947 internal analysis comparing the Niagara's operational costs against those of the EMDE-7 diesel units then operating on competing railroads, New York Central's Motive Power Department concluded that on the water-level route, flat, long-distance, high-speed passenger service, the Niagara's cost per mile was competitive with diesel within a margin that did not justify wholesale fleet replacement. The report carried a recommendation: continue Niagara production, build more, develop the next generation of the design, incorporating additional thermal improvements already identified by Kiefer's engineering team. The recommendation was filed. Additional Niagaras were not ordered. To understand why the recommendation was ignored, the institutional landscape of American railroading in 1947 must be examined as carefully as the dynamometer charts. General Motors' Electromotive division had spent the previous decade executing a sales strategy of exceptional patience and precision. EMD did not simply sell locomotives. It offered demonstration programs that placed diesel units on railroads at reduced risk, allowing operating departments to compare diesel performance against their existing steam fleets under live revenue conditions. The demonstrations were structured to highlight diesel's advantages: lower crew requirements, faster turnaround, elimination of water infrastructure, under conditions where those advantages were most visible. Railroads that completed the demonstration programs tended to order diesel. Railroads that ordered diesel began building institutional knowledge, training programs,
and shop infrastructure around the new technology. Each unit added to a diesel fleet increased the relative cost of maintaining steam expertise and decreased the relative cost of expanding diesel operations. By 1947, this process had already reached a self-reinforcing momentum on most major American railroads. The Pennsylvania Railroad had committed to full dieselization. The Baltimore and Ohio was deep into conversion. The Santa Fe had placed massive orders with EMD. The institutional infrastructure of the American railroad industry, from the parts supply chain to the training programs at mechanical schools to the financial models used by executive committees, was reorganizing itself around diesel as the assumed future. New York Central's leadership faced a question that was no longer purely technical. The Niagaras numbers were real. The 1947 analysis was honest. But the railroad operating in an industry that had committed to diesel was not operating in the same environment as the railroad operating in an industry still genuinely undecided. Suppliers were discontinuing steam-specific components. Insurance actuaries were adjusting their models. Young mechanical engineers entering the profession were training on diesel systems. The cost of maintaining steam expertise in that environment was rising every year, regardless of what any single locomotive's dynamometer chart said. Paul Kiefer retired in 1948. The engineering philosophy he had spent 4 years applying to the Niagara retired with him. New York Central's board, facing a landscape where every major competitor was dieselizing and where the institutional costs of remaining a steam railroad were compounding monthly, authorized full conversion in 1950. The scrapping of the Niagara fleet proceeded between 1953 and 1956. 27 locomotives were built. 27 were retired. 27 were cut up for scrap metal. No preservation campaign reached completion. The New York Central, unlike Union Pacific, had not cultivated its locomotives as public symbols. The 20th Century Limited was a brand. The Niagara was a tool. When the tool was superseded, the railroad's institutional logic applied the same calculus it applied to any surplus equipment. Assess the scrap value, compare it to the storage cost, and act accordingly. Museum inquiries arrived after the majority of units had already been processed. The few that remained in storage yards were in conditions that preservation organizations of the era could not address within the timeline available before the scrapping contracts were executed. The Smithsonian's transportation curator documented an inquiry regarding Niagara No. 6000 in 1954. The response from New York Central's Equipment Disposal Office noted that the unit had already been sold to a metals dealer in upstate New York. The most thermally efficient steam locomotive ever tested on the American continent left no physical evidence of its existence. The absence of a surviving Niagara creates a specific distortion in how the steam versus diesel transition has been understood by historians and the general public. The standard narrative presents the transition as technologically determined. Steam was inferior, diesel was superior. The market rationally selected the better technology. This narrative is supported, in part, by the artifacts that survived the transition. The locomotives preserved in museums are, with few exceptions, the locomotives whose operators decided preservation was worth the expense. Union Pacific preserved big boys. Norfolk and Western eventually preserved a J-class. Southern Railway preserved steam as an operational heritage program. These decisions concentrated the physical evidence of steam's legacy in locomotives that were famous, large, or institutionally valued for reasons beyond their operational performance. The Niagara was none of those things. It was the most efficient, not the largest, not the fastest, not the most spectacular. Efficiency does not photograph dramatically. It does not draw crowds to trackside. It does not generate commemorative postage stamps. The case for preserving the Niagara rested entirely on its documented performance superiority in the specific metric that the steam versus diesel debate actually turned on. And that case required access to the internal analysis that New York Central never publicized. The result is a historical record that systematically underrepresents the most technically compelling argument that steam ever made against diesel. The locomotives that survived the transition era are the ones that made their case visually and emotionally. The locomotive that made its case in dynamometer charts and cost per mile analysis is gone entirely, leaving its argument accessible only to researchers willing to excavate university archives. The University of Michigan's Bentley Historical Library holds the New York Central Railroad corporate records, including the motive-powered department files from the Kiefer era. Researchers who have examined those files in the decades since the railroad's dissolution describe a collection of documents that reads, in retrospect, like a quietly desperate argument for a decision that was never going to be made. Test report after test report documents the Niagara's performance in language that is precise, technical, and deliberately understated. There are no marketing claims in these documents. There are no appeals to prestige or history. There are columns of figures, miles per gallon of water, BTUs per drawbar horsepower hour, scheduled versus unscheduled shop time, cost per 1,000 ton miles, and the figures consistently make the same case. On the water level route, in the specific operating conditions that define New York Central's most important passenger services, the Niagara was competitive. The recommendation buried in those files, build more Niagaras, develop the next generation, represents a road that American steam technology never traveled. Whether a further developed Niagara, incorporating the thermal improvements Kiefer Steam had already identified in 1948, could have extended steam's competitive life on high-speed passenger routes by another decade, is a question that cannot be answered from the evidence that survives. The hardware does not exist. The next generation design was never built. The argument ended not because it was refuted, but because the institutional context that would have allowed it to be tested had already been dismantled by decisions made elsewhere in the industry. 27 locomotives, the most efficient steam engines ever tested in America, gone before the decade that produced them had ended. Today, a small number of railroad historians and preservation advocates are aware of the Niagara's record. The documents in the Bentley Library are accessible to researchers. The dynamometer charts have been cited in technical histories. The 1947 cost analysis has been reproduced in academic papers examining the steam-diesel transition. None of this has produced a physical object that a visitor can stand beside. The big boys stand in their museums, 8 survivors from a fleet of 25, drawing crowds that line up for hours. Their preservation was a decision, deliberate, institutional, and expensive, made by an organization that understood its locomotives as cultural capital as well as mechanical equipment. The decision to preserve them is why they exist to be seen, and why the story they tell, the story of the largest, the strongest, the most spectacular, is the story that most people carry when they think about American steam. The Niagara story requires a library card. It requires patience with faded documents and unfamiliar technical terminology. It requires the willingness to be persuaded by columns of numbers, rather than by the physical presence of a machine that has survived long enough to be seen. The most efficient steam locomotive in American history made the strongest technical case that steam ever made against diesel. The case was documented, preserved in archives, and completely ignored by the institution that made it. And then that institution scrapped the evidence. What remains is a question that the documents raise and cannot answer. If the Niagara had survived, even as a static display in a museum alongside its test records, would the history of the steam-diesel transition look different? Would the standard narrative of technological inevitability be harder to sustain in the presence of a machine that proved, in its own time, by its own railroad's own analysis that the outcome was not inevitable at all? The question has no answer. The machine is gone. The archives are open if you know where to look.